for coming along to this this presentation and for having us, and also for for the opportunity to talk about our work. This is going to be a bit of an ebb and flow presentation because I'm going to start and then hand over to Edgar, and then I'm going to take over again and then hand back to Edgar, and then I'll take over again. So but what we want to do is talk about the work that we've been doing on spatio-temporal modelling and anomaly detection in river networks, and we'll explain why that's a bit challenging, more challenging than the usual sort of spatio-temporal modelling that we might do, and also why the anomaly detection then makes it even more challenging, and what we mean by that as well. And we'd like to acknowledge our co-authors. So this project is undertaken in collaboration with Java Hoof, Erin Peterson, James McGree, and Daniel Isaac, and the people from the collaborators, international collaborators, and also from the Department of Environment and Science. And I just wanted to acknowledge the beautiful picture down the bottom, the Australia there. That's the rivers of Australia that's delineated there. So to the next slide then, because Edgar's just driving the slide so we don't have to swap. I want to just spend 30 seconds talking about our Centre for Data Science. So we, both Edgar and myself, were part of the Centre for Data Science. I'm the director of this. The centre has three types of activities. We have fundamental data science research, we have domain-specific data science research, and then external partnerships. It's a centre that goes across the university, and so has collaborations in mathematical sciences, statistical science, information science, computer science, and then the domains as well, with over 100 researchers, as you can see there. And if you go to the next slide then, Edgar, you can see here the different domains that encompass that are incorporated into the centre. And the reason for showing this is really about like the richness of data science, and how, you know, we have statistical science is really one of the pillars in data science, but then we're able to then collaborate with these other researchers and practitioners who are using data in very innovative ways and analysing those data in different ways. And so we learn from each other through our computer science and information science peers, and then also through to the work that's being done in the different domains. So if you go to the next slide, Edgar, we go further than that then. So in our Centre for Data Science, we've now established the Australian Data Science Network, which is this collaboration between the 25 or 30 different centres for data science now that are in Australia across the country. And this is really exciting, where we're starting to create this energy and profile in all of the states of Australia. And so if any of you are interested in presenting to the Australian Data Science Network or the Centre for Data Science, or collaborating or finding people who are working on areas of your interest, then we'd be delighted to connect you through this ADSN. Okay, thanks, Edgar. So I'd like to start by just having an acknowledgement of the fact that we live in this world now where there's all of these new sources of data. And so one of the sources of data that we've been working on, and we won't talk about this here, but I wanted to mention it just as an idea of this kind of, you know, new world that we live in as statisticians, and how we can really contribute to this new knowledge. And this is in the area of like citizen science. And so a project that we are working on is with virtual reef divers. So the Great Barrier Reef is 2,300 kilometres long, and it's a national, and it's a world treasure. But the problem is that we need to monitor it, and there's only monitoring stations at certain points of the reef. And so what do we do in the middle where there's no monitoring? Well, we can use satellite data, and so that's another source of data. And we can also then have people with their underwater cameras and also underwater drones. And so what we've done is create this virtual reef, Great Barrier Reef, and we allow these images to be tagged, geotagged onto the reef. So divers who take photos, and then we can upload those photos onto this virtual reef. Then we ask other users to go in and for each of those images, as you can see here, annotate the images according to what type of structure they see. So is it coral, sand, algae, and so on? And then we can take that information, their citizen information, and we can then incorporate that into our statistical models to get better coverage of the Great Barrier Reef and therefore better predictions. But one of the questions is, how trustworthy are these data? And that's really where the statisticians can come into play. So how do we make these citizen science data trustworthy? So to the next slide then, please, Edgar. Another source of data, so this is an example here of where we've been looking at how we can try to adjust the responses from the citizens to actually make those data more trustworthy. So the green line here is what's observed. So this is the responses that the citizens provide. And through modelling then, and we're happy to talk about these models afterwards if people are interested, we can then adjust for the ability of the respondent or the citizen scientist, and also the difficulty of the images that they are annotating, and we can then move that green line to the blue line, and you can see that's what we're predicting here, and then that's much closer to the red line, which is the truth. And so this is a way that we can then, as statisticians, use this new data in our predictions and also look to modify those data or like adjust those data so that they become more trustworthy. Thanks, Edgar. Another type of data that we're interested in is using video data and real-time data. And this is in the area of sports analytics as an example here. And what you see here is using this sports technology for the NBA. And what we're interested in here is, can we use, like, how do we analyze these data? There's a lot of this kind of video type data and tracking data effectively. How do we use this to be able to gain new insights into the system, like games, like sports? And so what we see here is, what we've done is we've used the idea of intrinsic dimension. So can we look for the kind of like surprise moves, or the consistency of the data, or the actual intrinsic dimension of the data? And we can measure that through looking at the ratio between an observation and its neighbour and its second order neighbour. And that ratio then has a Pareto distribution, and the parameter of that Pareto distribution is the intrinsic dimension, or can be considered to be the intrinsic dimension. And that can tell us about the predictability of the movements here, or the unpredictability of the movements. And you can see here, as the play continues, there is this change in the intrinsic dimension, or the unexpected movements, or the predictability of the movements as the game progresses. And this can be differentiate between home games and away games, between winning teams and losing teams, and gives us greater insight and richness for this data. So it's something else that Edgar has also been working with. So Edgar's been looking at the citizen science data. He's been looking at the intrinsic dimension and sports data. But what we want to talk about today is our work and Edgar's work in water quality monitoring. And this is to look at how we might use sensor data, so from the sensors that are in the water, to then be able to do this water quality monitoring. Of course, this is a really big issue even for the Great Barrier Reef, as we know, because if there's poor water quality going into the reef, then that's going to influence the coral on the reef. And also it's important for agriculture, it's important for all of life. And so we're interested in this water quality monitoring using these new types of data, the sensor data, but we know that these data as well need to be modified to increase the trustworthiness, because these data, the sensor data, are influenced by anomalies. So technical anomalies that mean we can't, that there can be signals in the data that are not due to water quality, but are due to these technical anomalies. So how do we understand what's a technical anomaly in the data compared to a real signal in terms of water quality? This is the team that's working on this. Thanks, Edgar. And just to show you then these sensors, so there's very high quality and very costly sensors, but there is increasingly lower quality sensors, and they are more prone to these anomalies. And the guy in the photo here, who's actually out in the field putting these sensors in the water, is Edgar. So he's a man of many talents. Not only does he work with different kinds of data and do amazing modelling, but he also gets out and does the field work as well. So we have two papers that we'd like to talk to you about. You can see here the references, and we'll give these at the end as well. So some of our modelling and then translating that into an R package. And on that then, I'm going to hand over to Edgar to tell you about the kind of models and work that we've been doing. Over to you, Edgar.
Thank you, Kerrie. Thank you, Ben, and the others for the invitation. It's a real pleasure to be here today. Next, I'm going to illustrate how do we model variables in space and time, accounting for the unique branching structures of rivers and streams. As Kerrie mentioned before, we are increasing the use of data from sensor technology. That technology is getting better and better, and we are basically getting data on kind of in real time. So basically getting data every 15 or 5 minutes. So the sensors, such as the one that I showed before, are recording multiple parameters. For example, those on there are recording water temperatures, turbidity, conductivity, the level of the water on the stream, and also other important parameters such as nitrate. So these sensors are basically placed on branches of a river network. So here we have a small network with four sensors. But how do we establish spatial-temporal dependence in river networks? So in this figure, what we observe in spatial location 1 is closely related to what we measure in spatial location 2, 3, and possibly 4. However, what we measure on spatial location 2 might not be correlated to the measurements that we have from spatial location 3 and 4. That's why, because they are not connected by flow, right? So even if they are close in Euclidean space, they are not sharing flow, and they may not have, the data might not be correlated. So so in this work, we are going to take that into consideration. So we are going to account for spatial dependence using covariance matrices that they are going to use stream distance, and they are going to consider factors such as flow connectivity and also the area around the branches. So here is a representation of the same network, but across multiple time points. So let's say t equal 1, 2, etc. And this is generally known as a time series of a spatial stream network process. So the objective here is to model variables in space and time, and also to make predictions where no data is available. Suppose that, let's say, spatial location S3 at time 3 has not been observed, and we want to estimate its value using, for example, spatio-temporal interpolation or kriging. The prediction is going to be conditional on what happened on the same spatial location at previous time points. So let's say t2, t equal 1, but also on the neighboring site. So let's say spatial location is 4, at the same time point or previous time points. In this work, we propose the following model. So we have a response variable y. That could be, for example, water temperature or nitrate. And we are going to express as a linear combination of some covariates plus some quantity v. And we are going to incorporate then in this parameter v a spatial dependence. And to do so, we are going to use covariance matrices, for example, combinations of different covariance matrices that account, for example, for flow connectivity and stream distance. We can also have covariance matrices that they use Euclidean distance, like the traditional geostatistical models. We express the mean of that process as a vector autoregression. In this case, it will be a vector autoregression of order 1, and is composed by multiple time series. In this vector autoregression, the key part is this parameter phi that is going to be a transition matrix and is going to rule the amount of temporal dependence that we are going to have. However, one of the problems with estimating this transition matrix is that when we have a lot of spatial locations, let's say 100 sensors, we get in troubles estimating all of those autoregression parameters. So that's why in this work, we propose multiple solutions for estimating that transition matrix. So we consider multiple cases, for example, starting from a very simple one that we call case 1, that is just an autoregressive process. In that case, all the off-diagonal elements of the matrix are equal to 0, and all the diagonal elements are equal to phi, and it means that the amount of temporal dependence in all the spatial locations is going to be the same. So this model is a bit restrictive, right? That's why we have a second case where we are going to allow to have site-specific autoregression parameters. And we have then two cases. So a second case where we are going to express that autoregression parameter as a linear combination of some covariates or spatial predictors. And a third case is going to consider, for example, if you look at the network on here, you might think that what we observe on spatial location S3 might be highly correlated to what we observe from previous time point on spatial location S4. That's why our third proposal is a transition matrix that is going to consider as well the two nearest neighbors. Right? So this could be, for example, the two nearest neighbors connected by flow, or the two nearest neighbors upstream from a given spatial locations. Then to incorporate then spatial correlation, we are going to use so-called spatial tail-up and tail-down covariance matrices that they have been previously proposed in the literature for modeling data on streams. And these covariance matrices are going to account for those factors that I mentioned before, such as flow connectivity, stream distance, and so on. The name from these covariance matrices, it basically indicates the direction of the tail of the autocovariance function. So if it is a tail-up model, it means that the tail of the autocovariance function, it points upstream. And in the case of a tail-down model, it's the opposite, right? So it's going to, the tail of the autocovariance function is going to point downstream. So to illustrate the use of these new methods that we have been developing, we are going to use a case study of daily water temperatures on the Boise River in the northwestern part of the US. So it's a quite large branching network extending over 7,000 kilometers. And we have on there 42 sensors recording water temperatures, right? So the objective from here will be to interpolate, let's say, missing values across in areas where there is no data, but also make predictions in time, so or forecast in this case. Here we have, in this graph, we have representation of the time series of water temperature that is going to be our response variable. But also we are going to consider a group of topographic or spatial factors, such as extreme slope, elevation, and cumulative drainage area as a covariates. We are going to capture annual seasonality in water temperatures using harmonic covariates, in this case using the first pair of harmonic covariates, the sine and cosine. And this pair of harmonic covariates have been found suitable to model this kind of periodic changes on water temperatures. We are also going to include air temperatures. That is a climatic factor and is highly correlated with water temperatures. So if we look on here, air temperature is in red. We see that both are highly correlated, water temperatures and air temperatures. A key detail on here as well is that we see that the water temperatures, the air temperature drops sometimes below zero. However, the water temperatures, they basically get truncated to zero because basically the water freezes. As we usually do, we are going to assess the out-of-sample prediction of our models. And to do so, we are going to split our data set with 80% for training the model, 20% for testing. You can see on here the panel data. We have data spanning over 5 years, and we have the temperature, the water temperature values, and we have some missing values on there due to issues with the sensors. And in gray, we have all of those observations that we are setting to missing in our testing set, basically to assess how good we can predict from this model. So we implemented this using a Bayesian framework, and we specifically use the probabilistic programming language STAN. We try multiple variations of models. So, for example, multiple options for temporal structures like autoregressive, a very simple one, or a more complicated one, such as a vector autoregressive. And then we are going to combine that with some special structures. So, for example, we can combine. We can combine, for example, an autoregressive process with a tail-down covariance matrix, and then we have a spatio-temporal model. So, in total, we have 24 model variations. Some pretty simple, the others a bit more complex. Here we have a summary of basically the model comparison based on prediction accuracy. So we treat all the models, and then here we are comparing them based on different criteria, such as WAC, root mean square prediction error, etc. We are also including here some qualitative factors, such as model complexity, identifiability. We are also adding computational time. So we wanted to provide this table for practitioners to decide if the priority of the project is to, let's say, have a model that is not too complex, or if the priority is then prediction, then can select based on that the suitable model. So we found out in all of these models that the prediction accuracy was between 0.5 and 0.85, which is substantially lower than what others have reported in the literature using the same data set. So from those models as well, we get posterior distributions, for example, for the regression coefficients. We get as well estimates of the spatial parameters. On here we have a comparison of the autoregression parameters for the temporal part. We can see in this model that some spatial locations have more temporal autocorrelation than others. You might be thinking, well, how good is the predictions from this model? So here is a comparison of the held out data, temperature values at the 20% of the data set, and what we are estimating from the model. If the models are perfect, all of these data points are going to lay on the diagonal. They are not exactly in the diagonal, but the predictions are pretty good. So pretty much all of these models produce suitable predictions. One of the nice things that we can do with this model is that we then can make predictions across the whole branching network, across the 7,000 kilometers. So here is the original observation data from 42 spatial locations. And then using techniques such as Kerrie, we then can predict water temperatures across the whole branching network. From the practical point of view, ecologies are interested, for example, on how temperatures can affect different species of fish. These networks are populated with native species such as bull trout and salmon. And they have found out in lab studies that juvenile bull trout get thermally stressed when the temperature increases above 13 degrees. Therefore, it's critical to identify branching segments of the network and the dates where the temperature exceeds the 13 degrees limit. One of the potential interventions in that case would be, for example, planting trees in the riparian zone. However, this is pretty expensive. Anecdotally, some other researchers have also suggested using beavers. The beavers tend to make natural dams, increasing water levels, and that then reduce the temperature. So using these models, then we can predict the probability of exceeding this 13 degrees limit, right? So on this figure we have here on the top, times the 7,000 times series of water temperatures across the 5 years. And the dashed red line is the actual limit. And here we have the full branching network. And in color, we have what is the probability of going beyond the 13 degrees threshold. So we can see that the main stem and the lower elevation ridges tend to have like a really high probability, mostly around the summer months. Right? One attractive feature from these models is that we have MCMC samples, and we can do like, for example, compute the proportion of non-suitable habitat for this species of fish. So on this figure, we show the posterior density distribution of the non-suitable habitat for bull trout during the hottest days of the year. For example, during the 14th of August 2013, approximately 36% of the network was above the limit. And we can translate that into the proportion of non-suitable habitats in kilometers, so for this, the equivalent of 2,600 kilometers. And I'm going to hand it back to Kerrie.
Yeah, thanks, Edgar. Just before we do move on to anomalies, I wanted to ask, just very briefly, can you just talk about the computational cost and the computational issues about this? So just very quickly touch on that.
Yeah, that's a good point. Thank you, Kerrie. Yeah, one of the main issues on here is that we have a lot of spatial locations. So in some cases we have, let's say, 300 sensors. And then we could have, if we have, for example, a non-separable model where we have combinations of space and time, sometimes when we have high frequency data, we ended up with a really large data set, and we need to then invert a covariance matrix that is, the dimensions is really large. So one of the issues that we faced then was we had to find ways of to model that in a better way. So at the moment we are using a dynamic model where we basically have the evolution of a spatial process across multiple time points. So we found in that way reduce substantially the computational time.
Okay, yeah, thanks, Edgar, and we can maybe pick up on that later as well. But I wanted to say you've got this fantastic model now, this space-time model, and we can predict out to all of these areas over space and time. Looks pretty fancy. There's lots of colours and probabilities and thresholds and that. But I mean, we're talking about these thresholds in the water temperature in the particular example you gave, and saying if it goes above that kind of threshold, then we need to do something. Okay, so this is a trigger. But as we talked about at the beginning, we're using sensor data. And so some of those triggers may actually be from the technical sensors, the technical errors in the sensors, as opposed to the observations that we care about, in this case, water temperature. So what if there are these anomalies in the data? How are you proposing, or how have we proposed to deal with those? So when we first heard about these, that was the picture there actually showed what we looked like when we were going, oh my goodness, how are we going to do this? But luckily we've got a solution, and we'd be pleased to know your response to this. So yeah, go.
So yeah, these sensors, they have several issues. So some of the common issues is biofouling. So basically something builds on top of the optical sensor, and that causes some sort of anomalies. And this is, for example, data from turbidity from one of the sensors that we have. When we get biofouling, we get patterns such as this one on here. So we start getting like a drift on the data. And that kind of anomalies are pretty difficult to identify. Other potential issues with the sensors are, for example, battery failure. Sometimes these sensors are on different sections of the stream, and sometimes they are covered by vegetation, or the solar panels, they have issues and the batteries don't charge well. And that causes issue with also with the sensor. Sometimes the sensors ended up outside of the water. There is like a flooding event or something like that, and they basically are washed out and ended up outside of the water. And all potential issues are calibration problems. So there is a lot of different approaches to deal with anomalies. But first, I'm going to talk about what are anomalies. So anomalies are basically data points that are substantially different from its non-anomalous k-nearest neighbors. So this could be on a space, this could be on time. So we use this principle then to try to identify anomalies. As Kerrie mentioned before, one of the issues that we need to consider here is that we have water quality events. So we may have like heavy rains or flooding events that basically affect the data that we have. And then, or we could have sensor anomalies, so technical anomalies with the actual sensors. And it's really tricky to separate the two things, right? So we need to consider that in our models. One of the benefits of modeling this especially is that we have multiple spatial locations. So ignoring this spatial correlation tend to produce biased estimates. So we need to account for that spatial autocorrelation in our data. And we have also multiple parameters in the data. And ideally, we should have a framework that is going to account or is going to be like a multivariate kind of approach. There's plenty of literature about detecting anomalies, a lot of approaches, methods, suggestions. Really common in the literature, so a lot of people use the extreme value theory principles. Some others suggest, for example, using time series outlier detection methods. for example, using ARIMA, or in some cases they use one step ahead forecast, and using ARIMA or time series model to detect anomalies. There is a large body of literature as well on statistical process control, dating back to the probably 1940s. So plenty of methods that have been used across the industry to detect out of control situation or anomalies in the data. More recently, some methods such as hidden Markov models have also been suggested to deal with anomalous data, right? So in our case, because we already have been building on this spatio-temporal model, we are going on, and our data is spatial and temporal. We are going to first apply our methods or fit our methods first, and then we are going to, from those models, compute the posterior predicted distribution, right? And obtain the residuals. And then we can do different things with that. For example, we can look, for example, at using mixtures, or we can use, in other cases, also hidden Markov model. So this is something that we are actively looking at the moment. So here, the response variable is determined by the latent states, and it's going to depend only on the previous time point. For example, in some cases, we could consider that we have two unknown latent states. So let's say a normal state where the data is nice and there is no anomalies on there, and a second state where we have anomalous data. And we want to predict the latent state of each observation. So the process is going to then move between the two states with some probability that is determined by some transition probability matrix. So we are at the moment in preparation of a manuscript. So we have been initially doing some simulation studies to see how well the models that we have been looking at can detect different kind of anomalies. So in the literature, we have found, and in our data, we have found that some anomalies are really easy to detect, such as, for example, large spikes. So like the data is normal and then suddenly you get a spike on the let's say, turbidity. That event is really easy to identify. We could have, for example, a shift on the mean. So we are, and then suddenly the process changes the mean. That is another very easy to identify anomaly. But then there are small cases such as high variability or drifts on the data that I showed before, like the data are drifting slowly, that are really, really difficult to pick up. And it has been reported in the literature that the methods tend to struggle to identify that kind of anomalies. So in this simulation, we are considering also the persistence of anomalies. So for example, if we have battery failures, the data seems to be anomalous for a large period of time. So we are incorporating that in our models, in our simulations. And here is some of the first results that we have got using this simulated data set that we have produced. That is quite similar to the data that we are observing from the sensors. On here we have multiple methods. So we have a benchmark that is an ARIMA method that has been suggested in the literature that is quite popular. And we are comparing that with some of the methods that we have been developing. So let's say using posterior predicted distributions. We have two cases. So first case is that we fit the model, and then those observations that are very off from the posterior predicted distribution, we suspect that they are anomalies. We classify them as anomalies with high probability. And we have a second iteration of that where we remove those anomalies and then we refit the model. And then using, again, posterior predicted distribution, we decide whether excluding those observations or not. And then some other models such as mixtures, HMMs, etc. And one last model where we borrow some principles from quality control as well. So we found out that this first model that's pretty simple, using posterior predictive distribution with 2 iterations, tend to have a pretty good multi-correlation coefficient. Also, it increased a little bit when we incorporate some principles from quality control. So now I would like to briefly talk about a second case study. So Kerrie mentioned at the beginning, or show an animation of one of the sensors that we are placing on North Queensland. So right on here, I don't know if you can see that. Specifically on the Herbert River. We traveled all the way from Brisbane to a town called Ingham, and we, in this branching network, installed 5 water quality sensors. So these sensors are recording really important parameters such as turbidity, conductivity, and level. And so we are getting high frequency data. So every 15 minutes, we get a reading from those sensors. Right? And so the data that we are getting, it looks like this. So the data can be a bit messy, and some of the anomalies are pretty obvious. Like on here, we see that we have a high variability on the right-hand side. We see on here as well that the turbidity basically drops suddenly and then start drifting. So that's something that is really easy to identify. But then we have other cases, such as this one, that looks like an anomaly, but is instead a water quality event. So that was an event that was observed simultaneously across multiple water quality sensors. So we could, looking at the other locations, we could say, well, that is not actually an anomaly; it's a water quality event. So some of our collaborators from the Department of Environment and Science, water quality specialists, they closely look at the data set, and they produce a labeled data set for us. So in this particular spatial location, so the first location here on the network, right on here. So they classify all the data over a period over two weeks, and they identify, for example, on here large sudden spikes suddenly on here and here, and they classify this as a water quality event, so there was not a sensor anomaly, and then they classify all of this region on here as a high variability in the data. And then from this point on, they classify it as a drift. So we then took that labeled data set, and the idea was to see how well the models that we are developing can identify some of these anomalies. So again, some of the anomalies are really easy to identify. Some of the others are a bit more difficult. So here are the results of using from the spatio-temporal model using a posterior predictive distribution with 2 iterations. So this model, on here we have, again, the time series in black, and in blue we have those observations where the model is suggesting with high probability that there could be an anomalous data points. So basically on this region on here, so it captures well the high variability on the data and also the drop on here, but then it misses the drifts. So that is a big limitation, because one of the priorities on the project at the moment is to develop models that can pick this kind of challenging anomalies. It also missed the large sudden spikes on these data points on here. So we repeated the same, but using hidden models. So with 2 different states, this model was substantially more sensitive. So it identifies really well the high variability, the all the drifts. So we are really happy with that, with the model identifying that. It also indicates on here that could be potentially an anomalous region on the data set. But after looking at the nearby spatial locations, we can easily see that there is a water quality event. And it also picks really well the two large soil spikes on here. So this is a work in progress. It's a large group of statisticians, ecologists, water quality specialists working on this. One of the objectives is to produce tools, free software. In particularly, we have been developing an R package that is called SSMBase. That stands for Spatial Stream Networks, and it uses a Bayesian framework. That's why the last name. So this R package lives on GitHub. It's also on Kerrie, and the main features of the R package that allows you to model or visualize stream network data in space and time. So pretty much all of those visualizations that I showed before, you can produce them using this R package. The central part of the R package is to fit spatio-temporal linear models and to make predictions. So use spatial stream network data and then fit models and make predictions across the whole branching network. If the topic is of interest, or you have data, or you could have a look to this notebook where we have a full reproducible example on there with data, visualizations, fitting models, making predictions. And again, if you have any feedback on how to improve that, please let us know. We are always happy to take on board feedback. Briefly, in the last minutes, we'll show the main functions from the package. So to fit a linear model on there, it uses this SSMBase function with the arguments that you are familiar with, as in base R, using the ELM function. We need a formula, let's say temperature as a function of some covariates. We need to specify a data frame, and optional, we need to specify a path to a spatial stream network object where we have all the information about the branching structure. If you don't have it, you still can fit models on there using traditional geostatistical models. And the other important arguments on there are where we specify the spatial and the temporal components. So if we use what sort of covariance matrix we are going to use, or what sort of vector autoregression, or what sort of time series model we are going to use. And to make predictions is easy as well. So we use a fitted model in STAN, and we have to specify as well a prediction data set where we have the covariates for the locations where we want to predict. And we can do this in parallel. So one of the, Kerrie was mentioning before, what some of the computational challenges with these models. So this function allows you to make predictions in parallel, just by chunks. Let's say if you have 100,000 spatial locations, it's very challenging to do that in one go. So we can do this by parts, let's say in chunks of 100, for example. Do you want to conclude, Kerrie, or do you want me to? You're on mute.
Okay, so I'll just conclude. So to do the ebb and flow. So the conclusions then, mainly what you've seen are that we've fitted space-time models, and we've demonstrated that these produce suitable estimates and predictions. We find that these tend to outperform time series approaches existing in the literature, and they have a good performance in the detection of anomalies. We're still working on this, and we understand that and appreciate that there are experts in this area in the audience. So we'd really like some feedback on this. Our future work is to look at space-time anomaly detection in real time, and to do some more work on trying to disentangle the anomalies from water quality events and those from the sensors themselves, and then to develop an integrated probabilistic framework for the persistence of these anomalies. So on the basis of that, then I'd like to, if you go to the next slide, please, Edgar. I'd just like to make acknowledgements of all of our collaborators for this work. And if you go to the next slide, please, there's some references here. And then finally, we have some of the papers, again, some references if you'd like to read some more about our work. And on that note, then I'll hand back to you, Ben.
Thank you both. That was a really fascinating and detailed talk on what's clearly a very, very challenging problem. So thank you both. I'd like to open the floor to questions now. So if you have any, please can you post them in the chat or raise your hand and we'll come to you in turn. So Owen, a question from you.
And Edgar, could you stop sharing, please, just so we can see?
So, yeah, hi, morning. So, yeah, lovely talk. I just had a question about extremes, because in river networks, very often we're interested in extreme events, flooding, for example, or pollution events, and very interested in how they're correlated. But of course, often the correlation structure you see with extremes varies from what you see for the bulk of the data. So I was just curious with the modeling structure you've got, whether you've looked at how well it picks up correlation between extremes in the data, or if it does.
Do you want to go first, Kerrie?
Off you go.
All right. So yeah, the data that we have, we started working, for example, with temperature data. So the temperature data is quite nice, despite you see these periodic changes in the time series. So that was really nice to develop the models. So we are now in a stage where we are using data from water quality sensors here in Queensland, where we have some of those extreme events quite often. We haven't been lucky enough to have those extreme events happening in those sections of the network in the time frame where we are studying, or in this case study. So hopefully later on the project, we are going to see when we have like massive floodings or heavy rain, so we'll be able to answer that question. But at the moment, our data doesn't, we don't have those extremes in the data so far.
Yeah, and I'll just add to that because Owen, sounds like you've done some of this work and have some suggestions for this. So we'd love to talk offline to you about it.
Sure.
Great.
Any other questions? So I have one to kick things off. I guess following on from what Owen was saying, really. So the covariance structures are obviously really challenging to decide, and you've tried a variety of different parametric structures so far, which are obviously driven by the application itself and what you know about it. I just wondered if you'd thought about trying anything non-parametric that might be able to deal with some of these isotropic differences through either both space and time, whether that's something that would be feasible in this framework.
So yeah, at the moment we haven't, that's one of the things that we have been discussing, in the sense that thinking as well that for when we have a lot of anomalies on the data, having something that is non-parametric might be more effective, and that probably will be less affected by having a lot of anomalies on the data. So mostly when sometimes we have 10% of the data has anomalies, and that substantially affects the model, and that bias completely our estimates of the model, like the partial seal and the spatial range they get all over the place. So one of the things that we're discussing now is to possibly have a non-parametric or something that is less affected by basically extremes on the data.
Great, thank you. Rob, got a question.
Yeah, thank you. Sorry, it's taking ages to unmute. No, thanks. I really enjoyed that talk. I've got well, possibly a couple of questions. The first one is, I mean, you mentioned, this is a problem we've come across as well. You mentioned when you've got air temperature as a covariate, which of course is a very strong predictor of water temperature, you get the different behavior when you get down to freezing points. And I mean, it looked like from what you're doing, you're modeling things as linear.
It's frozen, yeah?
I think that's a very poor description after what he's been talking about, Edgar, about reaching zero.
As from that Excel. Of course, that would be great.
Hopefully Rob will join us back in a second. Is there any other questions while we wait for that to happen?
I was wondering something. Have you considered functional data analysis? Just because I seen some of the plots and they reminded me of the course. But
the answer is we haven't considered it yet, but I think it would be a really nice solution, like have a functional. I think we'll be able to capture really well those periodic changes on water temperatures. As if you are aware of some developments on that, I'm really happy to hear about that as well.
I don't have anything in mind right now, but yeah, if I do have anything, I'll let you know for sure.
I guess one quick final question from me, if there's nothing else. Oh, Alan.
Hi. I was very impressed with the models used, but it seems to me that the Boise data had a lot of sensors in the upper reaches of the river, but then you were applying the model to the lower reaches of the river, where you had no confirmation. And this seems to me just a very dangerous thing to do, because immediately below your sensors, you might have anything flowing into the river. We live in the area where Southwest Water regularly put raw sewage into rivers because they're permitted to do so. So I have a general disinclination to extrapolate models beyond the area where you've collected data. So how would you respond to that criticism?
Well, that's actually a really good point. Unfortunately, we didn't collect the data. There's data that has been produced, that has been widely used. One of the motivations was because there has been a lot of development on methods using these data sets. And it was also the most detailed data set that we could find to develop our models. That's why we were inclined to develop the models using the data set. So yeah, really good point. We don't have many, we don't have special observations on the main reaches or the main stems from the network. And that's obviously a limitation. I suppose that being actually inclined to look tonight, I suppose that the variability of those predictions or the highest density intervals on those predictions in those regions must be really wide compared to the predictions on locations similar to where the sensors are. But that's a very valid criticism. Kerrie, do you have any?
Yeah, thank you. And it's a very insightful to see that. And I agree with what Edgar was saying. So we can look at some of the predictions and see what's happening. But you're right. And I mean, it comes to this area of like transfer learning or extrapolation. And there's a lot of work in the computer science area, as we know, on sort of transfer learning. And so what we're looking at in another project is sort of the statistical perspectives of that. So how do we do this kind of transfer learning from a statistical perspective? So watch this space, Alan, and in about a year's time, we'll be able to tell you.
Thank you.
Well, and if you've got some suggestions, we'd really like to hear them as well. Thank you.
Well, I think my suggestion would be if anyone wants to apply your model to, say, an ecological survey and show why fish are or are not in that part of the river, you've got to say, well, now we've got some predictions, put in a sensor and see how well they're validated.
Very good. Yeah, that's very helpful, and I agree. Thank you.
We've had a couple of questions in the chat. Oh, Rob, you're back. Are you able to, do you want to ask your question again? Try second time lucky.
I'm not sure how much of it came through at all or not. It would be the one time I would get chucked out. Yeah, it was about non-linearities, and particularly extreme ones, when if you're using, for example, air temperature as a predictor of water temperature, and when you get down to freezing, the standard close to linear relationship suddenly becomes very non-linear. And what, have you developed any ways of incorporating that in your models?
So I look at the first answer is that's why we put the harmonic covariates. Actually, I think that was like a couple of years ago, but we explore like having like a truncated distribution for the water temperature, like basically selling the model that the water is never going to go below zero. And I think I recall that there was some discussion about that, but we wouldn't go too far away in that direction. If you have any idea how to, I'm really happy to hear about that as well.
No, it was something we've been struggling with. So I was curious whether you'd found a really good way of dealing with it. So it's.
I recall that incorporating these harmonic covariates increases the prediction accuracy of the model. From the, I think one of the good things from the model as well is that even when the data is truncated, in the predictions, you get the predictions below zero. So for the rest of the branching network, even when the data is truncated at zero, the predictions are allowed to basically go below zero. But yeah, that's a very interesting. Thank you.
Yeah.
So
Sorry.
It's okay. I'm done. I'll leave it there. Thanks. Thanks very much. It was really good. Thanks.
So one quick final question, I think, from the chat. I'm conscious we're going over time. But essentially, Alex Bush has asked that you've got multiple measurements and whether there's any chance you can kind of combine those or use one to help with the correlation for the other measurements that you may be able to use. Hopefully that was the rough interpretation of what you're asking, Alex. So sorry if I've missed something.
In terms of, we are also looking at multivariate kind of statistics, such as the Hotelling statistic to model, like let's say simultaneously multiple response variable, like includes, for example, turbidity, conductivity, water level, and nitrate. We haven't gone in that direction yet. Kerrie, do you have any hints on that?
I'm muted. No, nothing that we've done so far. But looking at the question here, if we're looking at the, I think it's a really nice idea in that we can look at these different kinds of response variables. So thanks for the suggestion, and we haven't done it yet, but we will certainly look at it.
That's great. Thank you both.
Yeah, sorry, go.
There was another question. Yeah, I think somebody answered it in the chat. But Helen, do you want to ask your question, or are you happy with the answer that was given in the chat?
Yeah, it was just I wondered how we could use this model to, when the response variable is a count variable. For example, we had a number of fish captured, and Alex says that is supported, but he says that there were some problems. That it's not easy to model count variables using this model, and then Stephen asked that he was curious what the problems was, what the difficulties were with using count response variables. So I don't know if Alex can elaborate on that.
Can anybody hear me? My mic's not that great today.
Yeah.
Okay. I've tried using binomial versions of SSN package before, and it really struggled to converge poor predictions. I haven't done it with Poisson models. It wasn't count data, but and for clarity, this is a spatial model, not a spatio-temporal model. In fact, it was slightly temporal data, and I'm embarrassed to admit this, but so basically I tried to create multiple networks that represented different slices of time to try and incorporate all the data in one SSN. I don't really know if it worked because it didn't converge. So.
It may be more challenging to find a start guess for the binomial compared to a Gaussian response variable, especially if you have sparse data.
Yeah, exactly.
I think the idea of the time slices just is actually quite a good idea. I mean, you use that a lot in the sort of the dynamic Bayesian networks where if you have discrete time. So yeah, I think it's not so embarrassing to.
Okay, I feel better.
No, it's done quite a lot, and I think it's actually an interesting way to think about time and you know what the different structures might be at those different time periods. So yeah, it's good. But in terms of the model, the space-time model, Edgar, do you want to talk to that?
Well, yes, actually, Alex, if you have, if you could create like a reproducible example, we normally have meetings with the authors of the SSM package every Thursday, and we could look at that. At the moment, we haven't implemented on SSMBase models for counts, but we are basically using the same covariance structures that they use for the spatial part. So you might think that if the model struggles with that kind of data set, these other spatial temporals are going to be in trouble too. So also, if you want to, collaborate into that, we could put it into their package we are developing.
Absolutely, an offer of help is always welcome.
Actually, I think the spatio-temporal models might actually be quite useful because you are borrowing with some of the structures you're borrowing over time as well as space. And so when you were talking about Ellen, you were talking about the more sparse data, but then you might actually be borrowing from more neighbors, if you like, or adding more structure to the model. So it'd be interesting to see. At the heart of it, I guess, although we've looked at a particular distributional structure, you could conceptually, hand-wavingly, change it to in sort of GLM, but the devil's in the detail, of course.
Okay, well, I think that's all the questions we have so far. Can I extend my thanks again to both Kerrie and Edgar for that really interesting talk and such a long, detailed discussion of everyone's questions. As they said, please do reach out to them if you have any further comments or ways that you'd like to work with them again. And thank you very much for all the participants for joining today. I hope you found it useful. Thank you both.
Thank you. Thanks, everybody.
Thank you for having